Okay, I believe we're back. So today, like I said, I will be talking about complex roots. So this is having to deal with roots of high power, and so that means over 2, although this method of finding the answer still works for 2, it's just not significant. So now, if you've taken any minor algebra class, you know that when you take the square root of something, then you get, then you know that okay, let's just get an example. So let's say, hold on, I have to get paint. Let's say I took the square root of 2. So that's that. Let's take a perfect square. So let's grab 9. So we have the square root of 9, and so if you know basic math, then you know that this is 3, but it is also -3. So a lot of people say plus or minus 3, and those are both of the answers. So if you are doing anything that needs to encompass all the answers, then this is what you do. If you're just trying to get one of the answers, +3 will suffice. But so in most cases, the positive answer is okay. But what the point that I want to get across with this this idea is that there is a number of answers. So let's say there's n answers for every n power root you're taking. So n x. So there's n number of answers for every n power root you have. So what is interesting is that in normal classes, it is taught that if you take the cube root of something, so I'm going to clear this just for sanity's sake. So let's take the cube root of 27, because 27 is 3 cubed. So 27 cubed, or cube root. So what most people will say is that this is equal to strictly 3. And that is convenient for everyday purposes, but it is not the full picture. So what's happening here, and the reason that -3 is not included in this is because it is not actually an answer to this problem. If you cube -3, then you get -27, and that can be easily seen. So -3 times -3 is 9, but then 9 times -3, you only have one. It's a negative times a positive, so it becomes a negative. So what's going on here is that there are other answers to this problem that aren't being seen. And the reason that most people don't consider them in normal situations is because they are complex answers. So what I mean by complex is that they have imaginary numbers in them. So they fall under the category of a number in the format a plus bi, where a is the real component and b is the imaginary component. And so what happens with imaginary numbers is you can actually plot them on a graph, not a normal graph of x and y, but a graph of real numbers and imaginary numbers. I'm not sure if it's the actual terminology, but I'm just going to put the complex C here, just for just to have something labeling it. Like I was saying, you can graph a complex number. So the real component is a, so that's a, and the imaginary component is b, and so you get this point out in space that you can draw a line to, and what happens is you can find the so-called magnitude of this imaginary number, or this complex number. So the magnitude, if you know anything about vectors, is the length of this line. So it's the square root of a squared plus b squared. And so that will give you the answer to this. Well, that will give you the magnitude of this imaginary number. Now this will come back into play in a bit. So I just want to so I've mentioned so now that each root of a higher power has that many answers. So in this case, there are 2 hidden answers, and so we need to find them. So I'm going to clear the board here. So what happens is that there are other complex numbers that when you multiply them by themselves 3 times, then you get 27. And so there's a nice method to finding those complex numbers that makes it fairly simple to locate them. So we'll draw our graph here, and we can just remember that the horizontal is the real axis. So first we start out with, we know that 3 is an answer, right? Because that's just what we've learned, that's our intuition. So we can put, I'm going to grab blue here, we can put a vector that is right along the real axis that goes to 3, because we know that that's one answer. Now, there are 2 other answers, and what is the interesting quality of how these answers are oriented is that they are equally spread apart in terms of if you draw a circle with radius 3, then they will be as far away from each other as possible. So since there's 3 answers, then we can take the total amount of radians in a circle, which is 2 pi, or 360 degrees for those who don't like radians, and you can divide that by 3, and that gives you, well, that's the answer. So you can't simplify that anymore, but that's 120 degrees. So what that means is if we draw another line 120 degrees away from this first vector, and then draw another vector 120 degrees from that, and then we have 120 degrees left. So in total, it does the full 360, the full 2 pi. Then we can find what these other points are. And so you can see, because these have vertical components to them, they actually are complex numbers instead of real numbers. So since we said that this is 120 degrees right here, then we know that this in turn is 60 degrees because it's making a full line. So if we take the we can do this by sine and cosine. So then the sine of 60 degrees is let me write this out. So the sine of 60 degrees is root 3 over 2. And the cosine of 60 degrees, so I'm trying to not have you guys sitting here while I'm writing stuff out. The cosine of 60 degrees is equal to 1/2. So what we have is that we have 3 times this cosine, the cosine part, which is 1/2, plus the sine part, which is √3/2, times our imaginary component. And that is the answer. So we can multiply this out. It won't really change much. We'll just get 3/2 plus 3√3/2 times I. And that is our complex number that if we multiply by itself 3 times, we will get 27. So this is also, so the reciprocal of this number, which is just changing the plus sign to a negative, will also be a complex number just based off the symmetry of this orientation here. So it will also be a complex root of 27. So this can be done for any root, so it doesn't just work for our cube root. If we take a 4th root, then we have a circle with our origin in the middle. And if you know anything about 4th roots, then in most situations you would consider them just like square roots, other than the fact that obviously you take the 4th root of it, but there is a positive and a negative answer to them. And this makes sense in our idea. So we have the original root, which is right here, and then if we take 2 pi and divide it by 4, then we get pi over 2, which is 90 degrees. So we change the angle 90 degrees, and then 90 degrees, and then 90 degrees. And what happens is that the 2 real answers that we get are positive and negative. And this will happen for any even root, or any even, any even root. So since we're taking the 4th root, this happens because then it is a, because it requires, so 360 can be divided by 2, which is 180. So then when you take the 2 out of the even root and the 2 out of the 360, then it ends up giving you 180 at some point. So, but then all the odd numbers will miss this origin, miss this negative side of it. So the odd numbers are specific to what their starting sign was. So this is an interesting quality, and that's why we see that the positive and negative numbers play different roles. So then also we can see that for the square root, if you take the square root of a negative number, then, actually we have stuck of 5, so we should be seeing the optimizer kick in here. So if you take the square root of a negative number, then you get two answers that are imaginary. But if you took the 4th root of a negative number, then it would get a little more complex. So that's basically what I wanted to point out. There's also this idea with graphing these imaginary numbers of the Euler equation, which is nice just to know. I'm not really going to get into it too much, but I wanted to write it out for you guys. So the Euler equation is e to the I theta is equal to cosine theta plus I sine theta. And the reason that this is interesting is that you can actually, is that e to an imaginary power is actually a sinusoidal graph, and what ends up happening is because it's in this imaginary plane, it is a circle. So so what happens is e to the e to the I theta is just a circle of radius whatever the coefficient is here. And so originally it's a circle of radius 1. And so a interesting idea is that e to the I pi, so that's a rational number to an imaginary rational number of power is equal to -1. And this makes sense because if we have pi as the angle, then our cosine will be 1. It will be -1, and our sine will be 0. There'll be no imaginary component. So the angle here will just be 180, which is pi. So that's just something I wanted to point out. That's if you ever don't know the answer to something, this is probably the answer, just because it's so awesome. But I don't have too much more to talk about on this topic. I don't want to bore people with my droning on, trying to squeeze more information out of this when I am not the most versed on the mathematical community. So I will move on to my second topic, but in the meantime, I will play a short ad. So I will be right back.